Today, we're going to learn about vectors, okay? And we'll kind of buzz through all this stuff, and then we'll do some problems based on these ideas right here. But a vector, as it says, is a quantity which has both magnitude and direction, and represented by the length of an arrow represents the magnitude. So how long it is might represent like how fast the plane is going, or how much force is being put on an object. And direction. So a vector, unlike a line, which just has, well, a line has magnitude and direction, okay? But it's going in a line doesn't really have direction, but a vector is going in a specific direction. Like a force being exerted on an object, or wind. Wind has a magnitude and a direction. An airplane traveling, currents, if you're in the river or in the ocean or something, those are all kinds of vectors. If a vector represents a speed and direction of an object, it's a velocity vector. If it represents a direction and amount of force, it's a force vector. Directed line segment, meaning it is important that you're going from point 1 to point 2. So point 1 to point 2 is different than going from point 2 to point 1. Excuse me?
Does it have to be a straight line?
Yeah, it has to be a straight line. Okay? As initial point, the magnitude and the distance is the distance from point 1 to point 2. A zero vector is a vector that has no magnitude or direction. A unit vector, and people are a little confused by this sometimes, is a vector with a length of 1, but the same direction as the original vector. Okay? The unit vector is a horizontal. The unit vector in the horizontal direction is I, and in the vertical direction is J. Well, what happened? Where'd that go? So if I wanted to, so the unit vector, it would be something like B equals I plus J. So I indicates the X direction, and J indicates the Y direction. Okay, so this is not an imaginary number here. It just means the amount in the X direction. This is the amount in the Y direction. So in a unit vector, actually that's not right. Okay. So you could have a vector. This is not a unit vector. Okay. But a unit vector has a magnitude of 1, and we're going to talk about how you get a unit vector. Standard position of a vector is when the vector starts at 0, 0. A component form of a vector, A, comma, BI, the terminal point, meaning the end point, is A2, B2, and the initial point is A1, B1. That's where you start. And in order to find that vector, you subtract the 2's minus the 1's. We'll do some of these. And sometimes you write vectors in this form with these little, what do you call those? Those brackets that are kind of that shape. Okay? The magnitude of a vector is just like we've been doing. It's like the radius that we've been finding in polar coordinates. Okay? It's just the distance from one endpoint to the other endpoint. Okay, and that's the way you find it, by taking the magnitude of the, or you take the x squared. Basically, this is like x squared plus y squared, the square root. It's just like the Pythagorean theorem. We'll do some. Okay, a scalar product is a vector in which a component is multiplied by the scalar affecting the magnitude but not the direction. So if you have a wind going, I don't know, 10 miles an hour to the northwest, if I multiply that by 2, you would have a vector going 20 miles an hour still to the northwest. Okay. So now we can do some problems, right? So here we go. And I got to make sure I get to the last problem because it takes kind of a long time because there's a lot of algebra involved. Okay. Find the position vector P1 to P2 if P1 is -1, 2, and P2 is 4, 6. So graph both the original and the position vector. So to graph the original, okay, all I do is I plot those 2 points. So I go negative 1, 2, and then I go 4, 6, 1, I guess this is the 1, 2, 3, 4, and up 6, 1, 2, 3, 4, 5, 6, and I put a point there. And then I get a line. Oh, now I get to use my arrow tool, and I put a line that has an arrow on the end, and that would, it should hit the very end, but that represents that vector. Now, in order to find the position vector, I need to subtract the x's and the y's. So that would be 6 minus, whoops, wrong. I have to do the x's first and then the y's. I'm thinking I'm doing slope, which is 4 minus negative 1,
Those 2 lines before the
comma, what?
It's supposed to be a parenthesis.
Yeah, it's like a bracket, except to indicate it's a vector, you make it like an arrow, okay? Okay, 4 minus minus 1, and 6 minus 2. And so this vector is, the position vector is 3, comma 4, which means
That's 5.
5. I knew that. I was just testing to see who was paying attention. Okay, so that's 5, 4. So what the position vector is, it's a vector that starts at 0, 0, but it has the same magnitude and direction as this one. So if I went over 1, 2, 3, 4, 5, and up 1, 2, 3, 4, I would have a position vector that is the same length and direction as that one above, except it starts at 0, 0. You get that? Yes, sir.
Wouldn't you just move the start of the vector down to the origin and then move the vector down the start?
Yeah, yeah. So yeah, you could just slide it down that way, but you have to know what, you still have to do the subtraction. The other way I could have written this is equivalent to writing 5i plus 4j. It's just another way of writing it. Okay, so 5 in the I direction, 4 in the j direction. Okay? So, you ready?
No.
Can we move on?
Yep.
So the way you add and subtract vectors is you just add their x's and you add their y's, or their a's and their b's. Got it? And in the way you subtract,
not help that.
what?
Oh, no, wait, that's the very
And the way you subtract vectors is you subtract their a's and their b's. Okay? And so they are commutative, meaning you can go in either direction when you add and subtract vectors. And they're associative, meaning you could go A plus B and then add a C, or you could go B plus C and then add an A. It doesn't matter which ones you do first. Additive identity means if you add them together, if you add the positive of this vector and the negative of this vector, what do you get out? Hello. So if you add this, if you have, say this is B, and then you have negative B, you would get out 0. Okay, so if I add a vector, so this would be that vector going in the positive direction, this would be the vector going in the negative direction. If I add them together, my result is 0. Additive inverse property. Oh, additive identity. I think that's the additive inverse property. The additive identity property means that if I add the 0 to it, I get out the same thing. Okay, so that's that. Additive inverse means if I add the opposite, I get 0. Okay, so that's what that's all about. So hopefully I didn't mess up too much on my recording so far. Okay, so we're not going to do all of these because it's kind of a pain in the neck. So let's start out. So maybe we'll do all of them. Maybe we can make it a little bigger since it's hard to see. Is that hard to see? Because my screen is shrunk for some reason. I don't know why it's shrunk. But let's try to make these a little larger. That's better.
Larger than life.
So u plus v, to show how to add two vectors. V is the vector starting at, so if I started here and I went over 3, 1, 2, 3, and up 3, that would represent the vector v. So here is, and usually they make vectors with these lowercase bold letters. Okay, so they're kind of, that's how they indicate a vector. Okay, so there's vector v, and there, excuse me, I meant to do u plus v, didn't I? Not v plus u. Sorry, let's fix that. Okay, I erased it. Okay, so let's do u first, which I'm going to go back 3. Sorry, back 3 and up 1. So 1, 2, 3, and up 1. Sorry. So there's vector u. Okay. And then I'm going to add to that vector v. And the way you add vectors is the tail of one to the tip of the next one. All right. So I'm going to take vector v and I'm going to stick it over here. Okay. So I'm going to go from this point. I'm going to go over 1, 2, 3, and up 1, 2, 3. I'm going to put a point there, and then I'm going to make vector v. Okay. And you can see that the resultant vector is, this is called the resultant vector, this one right here. Okay, so if I went over 3 and up 1, and then over 3 and up 3, the net effect is that I'm going straight up how many? 4, right? And so u plus v must be equal to 0, 4, right? And we can check that algebraically to make sure that's true. What's 3 plus negative 3? And what's 3 plus 1? 4, and so it works. Okay? We're not in the movie theater here, okay? Can you stop chewing and making crunchy noises? Sir? Thank you. All right. Okay, so 2u minus v, I'll let you figure this out. So to find 2u, and oh, the other way I could have gotten here to show you that these are commutative, I could have gone v first, right? I could have gone over 3 and up 3 first, over 3 and up 3, and then I could have gone back 3 and up 1, and I would have ended up in the same spot. You see? Okay? So, whoa. So that's how that works. Okay? We're going to move on. So I'm moving on, and so if I want to do something like 2u minus v, oh, and it says find its magnitude. Well, in this case, the magnitude is just 4, but if I want to find that algebraically, I go the square root. The magnitude, we'll call the vector, the resultant, I don't know what we'll call it. Let's call it w, okay? So w, the resultant vector in this case, would be 0 squared plus 4 squared, which is equal to 4. It says find the graph it, find its magnitude. So 2u minus v, I would go 2 of these, okay? 2u minus v, I would go back 2 u's. So I would go 2u is equal to minus 6, what? 2, right? So that would be 2u. So I'd go back 6, 1, 2, 3, 4, 5, 6, and up 2. And there's minus 2u. And then I would, minus v means instead of going over 3 and up 3, minus v is going to look like back 3 and down 3, right? Okay, so that would be back 3, 1, 2, 3 more. Let's say this continues over here. So let's say that's 1, 2, 3, and down 3. So it would be, I go around this graph. And then, so that would be, so, yeah, so we're mixing together those graphs. So my resultant vector would be this one going from there to there, okay? So this one would be 2u, and this one would be negative b, and so on. And then to find the magnitude of that vector, I could do it algebraically by adding these two things together. So algebraically, this would be minus 6 plus minus 3, which is what? What's minus 6? Minus 9. And 2 minus 3 is negative 1. So if I wanted to find the magnitude of that, I would take the square root and the magnitude. We'll call the resultant in this case w, okay? Equals negative 9 squared plus negative 1 squared, which conveniently comes out to be, oh, it doesn't conveniently come out to be 82. It doesn't conveniently come out to be anything. Okay, so that's about 9 point something, right? 9 point whatever it comes out. Okay, and I'll leave that one as an exercise for the students. Okay. Whoa. No. Stay. Oh, cancel. Don't look at those grades. Quick. Hello.
Sam has an eye. What is mine?
Oh man. Okay. I guess I'm gonna have to record this video again later.
Yeah.
Okay. So that would be bad. So now you can goof around. I'm just kidding.
Can you cut that part out?
Yeah. Oh, I guess I could. Yeah, maybe I'll do that. I don't know how to do it. All right. I think I do. All right. So then you have find the unit vector. So to find a unit vector, what you have to do is divide by the magnitude. All right. So for instance, for this one, 4i minus 3j, which is the same as 4 minus 3 like this. I like it writing like this because it's less, but this is ij, or it doesn't matter. So the unit vector, so if I were to graph this, right, it says go over 4 and down 3. So 1, 2, 3, 4, down 1, 2, 3. Okay. So here is this vector here. All right? And then what? And then you want to find the magnitude of that, okay? So the magnitude of b is going to be the square root of 4 squared plus negative 3 squared, which this does conveniently come out to be, anyone?
5.
5. This is a 3, 4, 5 right triangle, okay? So the magnitude of this is 5. So a unit vector in the same direction of this as this, u, is going to look like 4i minus 3j divided by 5. In other words, or another way to write this is 4/5 I minus 3/5 j. Okay, let's erase this. And minus 3/5 j. So if I went over 4/5 and down 3/5, this is what this is telling me, is this teeny little vector right here. Let's change colors. I don't like. I kind of like a chartreuse. Okay. So that's not chartreuse. Okay. So this teeny little vector right here, you can barely see that. This one has the same direction, except I think I did it backwards. Okay. This one has the same direction as this vector, but its length or its magnitude is equal to 1. You understand that? That's what a unit vector is, and this becomes important later on. Okay? Is if I went over this way 4/5 and down this way 3/5, the length of this vector right here in the same direction as this bigger vector would be 1. Okay?
Really?
You get that? Okay. So, next thing, I think I'm going to have to save the big problem for next time. This one we can do though. Okay, so I'm going to have to cut off static equilibrium problem from your homework because not gonna have time to get through it because it does take a while. So, but we can do these types. This one is a lot of algebra. So, and I don't really want to rush through it because
Do we have enough space on our paper for all this algebra?
For this one, probably not. Okay.
What are we supposed to put?
What?
Static equilibrium.
Oh, did you do that in physics?
Let's just not do one stage.
I don't know.
So here is, this is called,
Yeah, we do.
Show off.
so when you're in this form of a vector, okay, you can have this trig form of the vector using the cosine. So if this is some angle, is that an alpha there? Angle alpha, okay, over here. And I know the magnitude of this vector, in this case, is 25 miles an hour, okay? I can break it up into its component form. So here, you use this to kind of go backwards, okay? So if you know an angle to be 30 degrees, and you know the magnitude of that vector, then you can break it into its component form, which is useful if you're adding and subtracting vectors, okay? So in this one, you have a ball is thrown with initial speed of 25 miles an hour. So that is the magnitude. Oh, it says what is the initial speed in the vertical direction and what is the initial speed in the horizontal direction. So you have to do this stuff a lot in physics, I bet. Any of you taking physics? Yes? So you go 25, and then you go cosine of 30. That's not very good. Cosine of 30 in the I direction plus sine of 30 in the J direction. Because of cosine 30, that's like, this is like x, right? So cosine of 30 is x over 25. So if I go 25 cosine 30, I'm going to get x. See that? So you just plug and chug. So you get 25 cosine of 30. You should know that.
This is 1.5.
No, root of 3 over 2 in the I direction plus 25 times 1/2 in the J direction. Okay, so you could simplify that a little bit. 25 root of 3 over 2I plus 25 over 2J. And that means that whatever that number is, 25 times 1.7, 12.5 times 1.7, you're going that fast in the x direction, or the ball is going that fast in that direction, and that fast in that direction, okay? And that's very important for figuring out, like, how long the ball is going to be in the air, or how long until it hits the ground, and stuff like that. All right? So, the next problem, which is static equilibrium, we're going to wait, okay? So, I guess I should pause my cutting edge video. What? Okay, remember you heard it here on Mr. Leader's cutting edge, so Leader's Edge Math Channel. And we'll be seen later tonight on the roller derby station.
Yeah, me not that.
Roller derby? So, the only problem, folks, listening out there in video land, the only problem that you can't do on your notes is problem 66, okay? So you can skip that one for tonight. We'll be back with that tomorrow. Okay.
Not gonna be here tomorrow.